Hello and welcome to Lecture 11. Today we're going to be covering section 2.4 from A General Introduction to the Art of Mathematics. So let's get into it. The layout today is, we'll cover that section I mentioned, 2.4, the content of which is about two-column proofs. So there's not much to say about that. I'll probably go into some generalities about that style of argumentation, and then we'll do a bunch of examples. I suspect that'll bring us up a little short of the normal time. I'd like to keep these videos to, so I've decided to include a little information about using LaTeX to typeset your mathematical writing at the end. If you're in a class where you're not using LaTeX or you're self-studying and you don't really care about that, that's obviously stuff you can skip. There won't be any mathematical content in that. So let's get going on two-column proofs. First of all, when do you use a two-column proof? They're suitable for situations that are relatively mechanical. You know how sometimes you do a bit of algebra to show that one side of an equation is equal to the other. There's a couple of applications of things like exponentiating and distributing and collecting terms, that kind of thing. The sort of sequence, when you were doing that in algebra, usually was a two-column proof, except almost nobody puts in the second column when you're doing algebra. Really, you should. As somebody who has to grade that kind of stuff, I really wish everybody was trained to put in that second column where you explain what you're doing. Um, Usually these kinds of arguments are used when you're showing two things are equivalent or sometimes equal. Not always, but generally they're used in settings where there's a limited number of sort of moves that one can do, things that are part of the axiom set for that area of math that'll let you transform objects in nice step-by-step way into one another. The first examples we're going to do are in logic, and there it's very applicable, but there are others. Certainly in algebra, set theory, relations, you'll find two-column proofs in a bunch of places. So I think I already said this. What the two columns consist of is one column where you do your work and the other where you explain your work. You say what rule allowed me to do that step. A couple of pieces of advice that I want you to think about, especially while we're going through examples, but later when you're trying to do your own. Try to be as step-by-step as possible. Don't combine a lot of things together. A lot of times, you know how annoying it is when your algebra teacher in high school would like skip 3 steps because they knew the stuff and everybody else was going, what happened? Well, you need to think that way about your audience too. You want to take it one step at a time. Just be slow. Explain every step. Do one thing usually in each step. Okay, but then again, I like this quote: everything should be made as simple as possible, but no simpler. Our proofs should not be ridiculous. I mean, these are still things that are meant for human beings to read. So what if we had, the commutative law is a great example. You have several things that need to be switched around, several pairs of things, maybe 3 different pairs of things that need to be commuted. Do you have to do that? Commute the first one, say that was a commutative law, then commute the second one, say that was a commutative law. You might be doing other junk, like something simple though, like regrouping with parentheses. You can do all that at once. Most people would do that all in one step and say associative and commutative laws were applied. And then you give your reader a little challenge. Don't expect them to make leaps of faith, but it's reasonable to do a couple of moves and have them look at it and figure out what it is. Watch out for the artificiality of the nature of being in a course on this stuff. Sometimes your professor or even if you're doing this in a self-study format, you want to show that you can do it in a totally one step at a time fashion, then follow the instructions, do that. I skipped ahead a little bit on the bullets, but this next one's a big one. Watch out for circular reasoning. It's maybe not quite what it sounds like. Circular reasoning, you sometimes get stuck in circles when you're doing two-column proofs. You realize that after a bunch of moves, you've just come back to something you had before. really is annoying when that happens. But that's not what I mean when I say circular reasoning here. Circular reasoning is essentially when you already assume the very thing you're trying to prove. Of course, you can cycle back to the thing that you were trying to prove if one of the first things you assumed was that thing. So don't do that. Um, Also, watch out for the appearance of circular reasoning. Now, why do I say that? A lot of times, I don't know why, it's just human nature. Maybe there's a temptation to write down first the thing you're trying to prove. You're trying to show that, maybe it's totally something simple like A and B is B and A. You write that down with an equivalent sign in between them. Well, that's wrong because you've just assumed, it makes it look at least like you've just assumed the very thing you're trying to show. So we're going to make sure we don't do that by two means. One is add in a sentence up front that makes it clear you're not just assuming this thing is true, but stating what it is you want to show is true. So we call those we want to show sentences. We want to show that the statements blank and blank are equivalent to one another. And then proceed with your two-column proof. You don't need any more intro than that. So that's one way. The other way we'll prevent ourselves from accidentally doing circular reasoning is never write down congruences. I give the same advice when I'm talking about algebra. Algebra students often want to write down an equality. If instead you always just write down one side or the other of an equality, you're safe from accidentally assuming something that's not true. The lines are things that are considered to be equal, or in the case of logic, equivalent. So put each piece of the calculation on a separate line. Excuse me, and you never use the congruent symbol. This is worth mentioning, but it's not a huge deal at first. You do want to have, at least as a subsidiary goal, the idea of finding the best argument you could. If you end up going around the barn, coming back to where you started, and then finally getting to the right place, there's a whole loop of stuff you could have eliminated. So, watch for that opportunities like that. If you literally go through a cycle of reasoning, cut out all that junk and just go the remaining part. So try to find ways to make your argument, what's the word, succinct. Get there as quickly as you can. Just don't leave stuff out, and don't combine essential steps unless, like I said before, they're the trivial sort where you feel like combining a few of them isn't going to lose the reader. And this is a good point too. When in doubt, err on the side of pedantry. I mostly just included this point because I love that word. I think everybody has heard the phrase being pedantic, like I'm being right now. When you overdo it on some trivial matters, that's called pedantry as a noun form. So, but this is a place for it. You're trying to make an absolutely perfect argument stream that goes from left side of an equivalence to right side of an equivalence. So if there's any question that you feel like maybe you're skipping a few too many steps, then you probably are. So let's get started with an example. We're going to show that A and A or B is equivalent to A or A and B. I have no idea if I pronounced all that right, but we're going to do this in two different ways. So let's proceed. I've got our normal window that has the calculator in it kind of set oversized, so we can pull this out here and do some handwritten stuff. You know what? Before I move it, I'm going to copy the logical sentences we want, at least one of them. So let me model the sort of thing I've talked about just now. First, start off by saying we want to show I feel like the word that can be put there. It's sort of optional. We want to show that A ANDed with A or B that's equivalent to A ORed with A and B. I'm going off the edge of the screen there a little bit, aren't I? Spread that out just a tad. Okay, so that's what we want to do. Now let's proceed to do it. So what we're going to do is start with one side. I don't see, oh, I do see something else though right now. I just noticed that I did a typo. And do you call it a typo when it's a writing though? This symbol right here was supposed to be an and sign. I guess I accidentally crossed my and made it into an A. Yeah, so A and A or B is equivalent to A or A and B. So yeah, let's start with the left side. They're roughly the same in terms of level of complexity, so that'll be fine. I'm gonna start with this and then ask you, remember the basic logical equivalences we worked on last time? Does any one of them look like it might be applicable? There's two, and that's why we're going to do this one in two different ways. So the first one I'm going to do is maybe some people were looking at this and saying, well, yeah, I should distribute. And that's pretty reasonable. So let's distribute. We would get A ANDed with A. That's, let me just kind of illustrate what the distribution law looks like. This is written out in the Giant book a bit, but we didn't do it in last lecture very well. So both the A and the symbol that it's attached to, the and sign, or the symbol between it and the thing in parentheses, both those things have to come out and go in front of the variables that are ORed together here. So that's why I'll get A ANDed with A, like so, but I'll also get A ANDed with B. And what goes in between these things is the symbol that was there before, that was inside the parentheses. So that A and goes in front of the A and the B, and this or here is what ends up being right there. That's how it physically looks or feels when you're doing this. I've made a mess on my proof. What rule did we just use? It's fine to abbreviate. That was the distributive law. If I had a slightly wider margin here, I would probably write it out, but since it's tight space, I'm just going to say dist. All right, what looks like the next thing we would do? Probably most people are looking at that A and saying, yeah, that one can be combined. That's really a single A. So we've got A ORed with A and B. And do you recall what that was about? This thing is one of two possible things that looks like a power. That's A times A, or A and A. And so the rule that says there really are no powers, or that things are their own powers, is called idempotence. So just probably IDEMP is enough. Idempotence. Great. Are we there yet? Crap, we are. Awesome. So I'll mention that the first line is often, if you put an explanation next to it, you'll say that's given. And this is the desired result. You don't have to have those. Sometimes I put them in, sometimes I don't. Usually it's clear to people that you're going to start with where you start and you're going to end with where you hope to end. So, labeling them may be redundant. All right, so that's one approach to the inequality or the equivalence we just had. There's another, which is perhaps quicker. No, actually, they're the same length, but it's less writing for sure. You see, A ANDed with A or B, we could have also used the absorption principle. So that's equivalent to just A, and that's absorption. And then also by absorption, that's equivalent to the other version of absorption. The disjunctive form is A ORed with A and B. So just two applications of absorption get us to that same thing. All right, well, that was a good first example, I suppose. We do want to look at ones that get a little more interesting because, if they were all just 2 or 3 steps like those, it wouldn't be much fun. So here's a pile of them. I think it might suit us best to, sorry, I'm going to resize this window and put it over on the side so we can see those. And we'll bring this guy out front and make it big. Right. So the first one on there, on that list of examples, is actually directly out of the text of Jayam. But it's still a good argument. I'm not going to throw off the "we want to show" sentence right now. We'll just get to the meat of it. So we start with, I want to make sure my pen is in about the right place to start. A ANDed with B or not A. Now, keep in mind that our goal is to eventually get it to look like A and B. Right? So what are you going to do? I'll just point out absorption does not work here because, well, it's got the right pattern where there's an and on the outside and an or on the inside, but the things on the outside have to match exactly with one of the things on the inside. Here it's A and not A, and that's not going to cut it for absorption. So we can distribute though. That's legal, and we would get A ANDed with B, ORed with A ANDed with not A. And, well, I already said it, but the justification for that is the distributive law. What can you do next? Well, I bet everybody notices this. This is a place where a sentence and its exact negation are on either side of an and. That's one of our laws. It's called complementarity. Excuse me, spoke into my hand. Complementarity. So what is the truth value of A and not A? When you have the complementary things, the statement and its negation, it just depends on what's in between them. If it's an and, you'll always be false because and needs a true on both sides to make it true, and this is never going to have that. Right? Whenever A is true, not A will be false, and vice versa. So this statement is contradiction. Is a contradiction, I should say. So then we have A and B ORed with little c. And the way we got to there was the complementarity rule. I'll just, again, abbreviate things. Well, then what happens? This is C ORed with the very thing we're hoping to get. Notice the thing we're after is just A and B. Is it right that C ORed with A and B just is A and B? Yes, it is. And what rule is it that allows us to do that? ORing with a contradiction has no effect, or it's like the identity. This is like adding 0, right? So yeah, you get A and B. Once I'm at that level, I no longer need the parentheses that were above, right? Because there's just the single operation there. So identity law. So we went from the thing on the left, I should highlight it. The thing on the left was this, A and B or not A, and then we ended up with the thing on the right, following a sequence of pretty simple steps. And so that's what you want to do. All right, let's push on and do the second one there. I'm doing a lot of examples in this lecture, because I don't know that examples are necessarily the best way to teach, but showing you how to do it is a good first step. You are not going to get this, though, unless you take it seriously and do some of these kind of problems yourself. So really, if you haven't been, the sort of person who tends to do their homework, now's the time. There's a nice big list at the end of the section in Jayam. I guess it would be page 90 or 91, where there's, I don't know, 10 or 12 different examples to try. So, go ahead and give them a shot. Do some of them. All right, so the second one here, again, one side is very, very simple, A, and that's apparently equivalent to all of this other stuff. It's kind of a surprise, isn't it? So we'll start with the complicated stuff, and then we'll try to reduce in complexity until we get to something, really simple, A. Okay, so A ended with, I want to watch the parentheses here. There's an opening parenthesis, and then there's a pair of things in parentheses just inside of that. A or not B, word with, and then there's another group of things in parentheses, right, before we get the final ending parenthesis for this whole group. So we have A or B, and that's second one's the close. Just trying to be careful and describe to you the kind of thinking you do to make sure that you've matched parentheses. Okay. Well, what are we going to do? Here's something I notice, and I don't know whether this is the best thing to do or not, but that second half that's in parentheses, the thing after the A and then there's a group of two things in parentheses, they both start with an A, and they're both or statements. Could I just distribute them out? I'm giving you that funny look because you can't. Why not? Think about why that's not really a place where you can do the distributive law. Distributive law requires two different operators in the pieces. And we would sort of be using the distributive law backwards here, but it's just not applicable because that's an or, and these things are ors as well. So it's not going to go. What can you do in here? Well, now that you notice it, everybody inside the big set of parentheses is an or. So we can commute and we can reassociate in pretty much any way we like. Okay? So I'm going to go hog wild and do a multi-commute and multi-associate thing here. You can re-express that as A, and we'll have A or not A, bringing the A and the not A. Sorry, that's not a not. A and A. Bad speaking too. A or I wrote bad and I spoke bad. I'm upset. Anyway, A ended with, what's inside the parens is A or A, ordered with, now we would have the B and it's not B or B. And how do you justify what we just did? If you do lots of commutative and lots of associative stuff, you can call it the generalized commutative and associative operation. I don't have enough space for that, so I'm just going to say com and assoc. Really kind of being a bad person right now, because when you're doing two-column proofs, there should be two columns, and I'm giving the second column very short shrift, but I want to write the other part big enough that you can see it well. So, all right, we could do this in two steps. I think I will do this in two steps because the things are entirely different. We're not just talking about reordering and regrouping things. A ordered with A, that's A because of the idempotence law. And then we'll leave this to do in the next step, but we probably recognize that not B or B can be simplified. All right, so what did I use there? Idempotence. Right, okay, and then I already foreshadowed this. We're also going to want to simplify the not B or B, which that's an or around two complementary statements, so that becomes true. At least one of those two is always true. If one's false, the other one's true, and vice versa. So there we end up with A ended with A ordered with tautology. That was complementarity. Oh, really, we're quite close now. Might as well deal with A or with tautology. If you or with a tautology, that doesn't affect the output. It's just the same as A. So that is A and A. And we can completely drop the parentheses at this point since there's only a single operation. Right? The rule that we used just now was called the identity law. And then finally, another example of idempotence. A and A is just A. Um, a moment, I think, about this first step that I did. I went from A or not B in parentheses, or with A or B in parentheses. If you were asked to do it in an entirely step-by-step fashion, could you? You should see the commutation that we really needed to have happen. And I point at this. I point at it with two pens. See how the A and the not B are there? But in the next line, I need them here. So what you really need to do is re-parenthesize so that you get those guys together. Then you can switch them, and then you can do some more re-parenthesizing. So it's really only one commutation, but there's a couple of reassociations before you're allowed to get to that commutation. My preference would be to skip over that sort of fine detail, but ask your professor what they want of you, because they may want to see at least at first that you can do it in a totally step-by-step way. The next one on this little laundry list of things we want to work out has an implication in it. Okay, so it starts with the sentence A and B implies C, and it ends up with not A or not B or C. Okay, seems hard to see at first, but I guess this is mostly a point about if you've got implications in the first sentence and then you don't have implications in where you're trying to get to. Right? This guy here has an implication. That one there does not. We're going to have to get rid of that implication sign somehow. The only tool we have at our disposal for that is the equivalent form, the disjunctive form of the implication, which is the not of the antecedent ORed with the consequent. I love saying it all grown-up style like that. You not the if part and you OR it with the then part. That's the equivalent disjunctive form for a conditional sentence. A lot of abbreviating there. Equivalent is also abbreviated. Okay. Then what? Look where we want to be. Not A or not B or C. Look where we are. Not A and B. Oh, but you know what? That almost looks like it's begging for us to apply De Morgan's law, doesn't it? You have the not outside of some pair of things hooked together with one of these ands or ors. Yeah, so let's try that. We'll get not A and not B, and then just copy down the rest of the thing, ORed with C, and just use De Morgan. And then where did I want to be again? I wanted to have not A and I messed up. Wow. I should probably just refilm this, but got to be more intellectually honest than that. Do you notice how I messed up? This is humiliating that I did this. Do you see what it is? Yeah, that symbol didn't get flipped upside down. When you have the negation of an and, it turns into an or. You probably spotted that. Actually, there's a stick that I sometimes do in classes where I intentionally mess up in order to see if people are actually paying attention. To be honest, this was not that. I literally just messed up, but okay, maybe I should have. Now I'm messing up by. Oh, this has gotten too meta for me to follow. All right, so are we there? Not quite. We want it to look like that. Not A or with, not B or C. Oh, but that's fine. The only difference between those two is how the parenthesization is. And we can just one application of the associative law get to it. Not A or with, not B or C. Groovy. I really should apologize for my handwriting. Looking back at it, it really stinks. Anyway, that's what it is. One more of these, and then we'll actually be done with our examples of two-column proofs, I think. Let's see. I'm looking at the count on the slides, and it would seem like there's more, but let's go. Again, this last one involves an implication, and somebody messed up in the way they put in the parentheses. So that should have been not A. See how it's an open parentheses there? Not A implies B and C. And then there's a closing parenthesis. That much is good. But then you've got the equivalent side. And so we're sort of finished, and there have been two opening and only one closing. So that's a typo that should have been fixed. Maybe I'll fix it in the slides before I post them for you. You'll have the good ones when you're taking notes. If you're taking notes, I don't know if people are using those, but I have been keeping the slides or the handout version of the slides linked in the descriptions of these videos. So if you want to kind of read along with the slides or make notes on it as you go, it's a resource that's available for you. All right, well, we'll start with that, and we want to show that it's equivalent to this other thing, but I'm not going to write that other thing down. That would be the circular reasoning thing that I was warning you about. So this is what was given. That's our left-hand side. We're going to turn it, first of all, into the equivalent or form, the equivalent disjunction. So that involves negating the if part. Connector becomes an or, and you leave the then part alone. Can I just say equiv disj? And you'll know what I meant there. Equivalent disjunction for the implication or for the conditional. All right, A or B. You know what? I'm feeling pretty good about this. We're almost there. What is standing between us with A or B and C and where we want to be with that expression? It looks to me like that's just a distribution law thing. So again, remember you take the A and the or sign that's attached to and put them both in front of both variables. You'll get A ORed with B, and then you'll get A ORed with C. Group those things, and the connector between them is the one that was in between the B and C. So that's an and. So we're done with that. I do want to point out there's a second step you can take here, which is kind of amusing, I think. But what we just used was the distributive law. And we're finished. Let me do that one more step, though. This is the and of two different disjunctions, A or B and A or C, right? And both of those can be written as conditionals, because ors can always be re-expressed as conditionals. And if you were to take this one step beyond, it would become not A implies B. The first one would be, and not A implies C. And that's actually a really obvious thing given the initial sentence. Look at the initial sentence. not A implies B and C. How is that different from saying not A implies B and not A also implies C? Yeah, they are kind of obviously the same. It didn't ask us to do that, but I just, I saw it and I had to put that out. Okay, let's get back to looking at our slides. We can switch these guys around now. Oh, so the next section is just some commentary and help on using LaTeX. So we're going to be using Overleaf here, but there are other options. One thing that I definitely think is a good idea for people who are going to be math students is to go ahead and download LaTeX and put it on your personal computer. There's sort of two elements to it, but usually if you download and install the graphical interface, it'll also go out and get all the files that it needs. LaTeX comes, just said it wrong. LaTeX comes with a lot of ancillary files that allow it to do all the stuff that it does. This is a moment where I should go ahead and straighten out something about the name of this software. The original package for typesetting math was called TeX. And TeX was created by a man who's a personal hero of mine, Donald Knuth. Knuth is probably considered a guru by people who do coding. He's one of the best computer geeks in the world. He pronounced this, I guess he was thinking about text, but he wanted it to have a different pronunciation so that it would stand out. So he could pronounce it tech, like in technology, tech, with a K or a CH sound. Then another gentleman came along, Leslie Lamport, and he took tech, which was, while it was an excellent program and probably one of the most single bug-free programs that has ever been written, Lamport wanted to have a slightly easier user interface. So he wanted to make it make structures that allowed it to just be a little easier on the typist when you're writing tech. And so he created LaTeX, which is actually written in tech, and you can get LaTeX and you can put it on your personal computer, and then you'll be able to do the same stuff I'm going to show on Overleaf. If you're in a class where your professor is having you do writing assignments, a thing I typically do with my Intro to Proofs courses is have everybody keep a little portfolio of some of their arguments, some of their proofs, so that by the end of the course you've got like 12 proofs that you've honed. You've really made them nice, and you're proud of them. So it's cool to have that little portfolio. So I find that using Overleaf is a really good way to do that because you have a certain capacity to share things back and forth, and I can put comments in your LaTeX source and things like that. But you can also benefit greatly by having it right on your own machine, so you don't have to have internet access while you're checking up your notes. Okay, so the first thing I want to point out is vanilla LaTeX doesn't do everything you want it to do. Can't quite grab that screen. There it is. So this is the document we started the last time I talked about Overleaf a little bit. We opened up one of their example documents, and then we made a few changes to it. This what's in here right there was exactly as it was in the example. I've added this line, use package AMS math. That is the syntax you'll use whenever you're looking to get at some functionality that's not present in vanilla tech or vanilla LaTeX. So the AMS math package adds in a couple of things, most notably a bunch of symbols that you'll need. So that happens, that use package command happens before you encounter this thing where it says begin document. And the whole portion of the document that's above where it says begin document is just preamble. And it's literally called the preamble to the LaTeX document. So we put in meta information like the title of the document, the author, what day we're doing it, or at least what month we're doing it. You don't have to have a date, to be honest. But we'll also sometimes we'll create our own commands. Anything that's not actually part of your writing usually put up here in the preamble. Okay, so when we did this before, I just wanted you to see the input code big, but let's resize this window a little bit so that you can see the output. You take this code, you hit compile, and output comes out. Now, there's a couple of things that I want you to, sorry, let me sync with the slides. There's a couple of things I want you to know about. And one is that this system has a lot of junk in it. It's too complex for you to expect to just memorize everything. I've been playing at it for a long time, and I still keep one of these around. This is, well, you can tell from the URL, this is stolen from somebody at the Brown department, math.brown.edu, so the math department at Brown. I don't know who JHS is there, but I thank him for compiling this thing because it's an excellent resource. Typically with computer languages or programs, you find people have made these cheat sheets, and they're usually a page. And that's the sort of the ideal, is to get it all into one page. This is 4 pages. It's big. There's a lot of stuff going on, and there's a lot of things that you can do in a LaTeX document. So, yeah. So I would recommend finding a good cheat sheet like this. I think this is a pretty decent one, and learning to use it. Some of the things that are in here are things like symbols that you might not know how to get it, right? So I don't know what to show you. We did the binomial coefficients at one point. Remember that? Binom? Well, there's a LaTeX code for it. /binom, and then n and d are both in curly braces. It typesets it like that with the parentheses and n over d. That's probably so tiny you may not even be able to see what I'm pointing at. Should I? Can't seem to zoom. Oh, here, there's a graphical zoom. That's the thing I was referring to. Binom, n and d gives you a binomial coefficient. You can see all these operator names: arc, cos, CSC, cosecant, exponential, cur. You probably haven't run into cur yet, but that stands for kernel. Unless you've done linear algebra, you've talked about the kernel of a linear map. Lim inf and lim sup, that's for later too, but when you do real analysis, you'll be glad that LaTeX can make those symbols. So yeah, I'm not going to get overbearing on that bit. There is something that it is worthwhile for you to get under your fingertips if you haven't had it before, which is the Greek alphabet. We have 26 letters in the Latin alphabet, which seems like a lot, but turns out when you're doing a lot of math, you can quickly run through all 26. And then you have an option. A lot of times people will put sort of funny decorations on the letters, like put a little hat on an A, and that's different from regular A. I personally like to just move to Greek if I run out of Latin letters. If you run out of both Greek and Latin, then you start throwing subscripts at things. But there's 24 letters in the Greek alphabet, so that's a lot extra. You'll notice that some of the letters, like alpha, renders this way as the little. That's one image, so I can't highlight it. But the thing that looks more or less like a lowercase a in script, but a capital alpha looks like a regular Roman alphabet. So the Romans borrowed that letter, right? The capital A, there's no need for a separate LaTeX command to create capital alpha because it's just the same as an A. Same as with beta and B. But gamma and capital gamma, those are, in capital gamma, neither of those appear in the Latin alphabet. So /gamma is this thing that looks like a hangman diagram. That has survived in Cyrillic, and it is exactly the Cyrillic letter that has the G sound, the guttural G sound. Delta looks like a D with maybe a little calligraphic D, but remember the triangle version of delta? A lot of times you use that in calculus for the change in some quantity. Delta X, right? The change in X. Um, there are two different versions of epsilon. Standard epsilon, which looks a bit like the foreign, is in the subset. Is it? I'm having a hard time saying that. The in a set thing. It's not quite the same. And then there's a variant of epsilon slash var epsilon. If you don't like the looks of the regular epsilon and you want to use that, use var epsilon. Personally, I always use var epsilon. Okay, so we've gone A, B, G, D, E. Z is not at the end of their alphabet. Crazy Greeks. Now, first of all, the lowercase zeta, I don't know what that is. It looks a little bit like a snake to me, like it's about to strike. But capital Zeta is a Z, so there's no need to have a special symbol for it. If you didn't know this, it's time to notice the thing that does occur at the end of the Greek alphabet is the letter omega / omega. So if you ever hear people say alpha and omega, it means the beginning and the end, because it's referring to the first and last letters of the Greek alphabet. I'm not going to go over all these things, but what I'm suggesting to you, this is right there in the Overleaf help stuff, is you should take a little time and learn the Greek alphabet. It's not that hard. And much of it you already know. And to be honest, there's a lot of these letters we never use. Lambda we use, mu we use, theta we use. Etas, rarely. I don't see a lot of etas, except in physics. Physicists tend to use them. Upsilon, they don't ever run into that. Ooh, I should have gone far enough that I got to sigma. The sigma sign, man, that's the summation sign. Why is it sigma? Because that's the Greek letter for S and sum. You get that? Yeah. The one thing that is annoying to me is omicron. The Greek letter for O doesn't have either one of its things called /omicron because they're both the same as they're rendered in Latin. So we just use little o and big O. Sad. Oh, there's another letter that is very uncommonly used, xi. I haven't spotted it. Oh, here it is. So it's a little hard to say. You like make a K sound and then say C, xi, but you got to run that together, xi. So it looks like a weird E in lowercase, and it looks like 3 bars, I guess, just 3. It almost looks like a Korean symbol or Chinese. I don't know, but it is a pretty rare one to encounter. Nu is not so rare. You see that fairly often. Well, pi, we see that all the time. A note on pronunciation, because I just did it. I said pi like everybody else does, but I have a friend who's Greek who told me that all of these letters that have a whatever with an I on the end are pronounced with a E sound, xi. So this really should be P. I think the Greek people just got tired of all the Americans chuckling when they ran into that. So a lot of people say pi now. But phi and chi and psi. Okay. What else? I talked about the cheat sheet. We just talked about the Greek alphabet. Let me show you one last thing, which is I'll show you how to write a 2-column proof in LaTeX, and then we'll call it a day. And that is using something called the align environment. I'm showing you the Overleaf help on the align environment. This is one of the things that's defined by that AMS math environment or the package rather, that we pulled in. It's often the case that you want to do something like what this displayed pair of equations are. You have 2 equations and you want them to line up on the equal sign. That's what the align environment is for. You put a little and sign down and say, okay, this equal sign is the middle. And so when it renders everything, it does what you were after. And you can use the align environment for things beyond that. For instance, look at the code that they've shown here. X, the alignment symbol is the ampersand equals Y, and W, alignment equals Z, and the line break doesn't matter, so this is still part of the same line. A, alignment equals B plus C. So that creates X equals Y, Y equals Z, and A equals B plus C, separated from one another nicely. And then you notice the other stuff that's underneath of it has got the same rough skeleton, and all the things vertically get aligned in nice columns. That's pretty, right? Well, we're gonna cheat to use that alignment feature to make our two-column proofs. So here is the source view of a two-column proof. You slash begin align star. Oh, I should mention the default version of things that look like begin align. There's one called gather. There's another one called just equation, begin equation. If you use the default one, LaTeX is going to create a number and typeset it in the far right side of your document. If you don't want everything numbered, and most of the time you don't need that, then use the star variant, which skips numbering your equations. So what have I got here? I've got an alignment symbol, and then the text for, well, let's go that far. The text for A and B implies C. Well, what's the difference? I mean, slash implies makes sense. That's the arrow. The and symbol is not created with slash and, it's created with slash land, because there's another place where we have and. And so this means logical and. We're doing logical and land. A land B implies C. Great. And then I have an alignment symbol, and then I put in some horizontal space. H space means that. So, sorry, I should readjust this so it doesn't break the line. H space of 3/4 of an inch, 0.75 inch. I picked something that looked about right to me. Another align symbol, and then the explanation for where that came from. That was the given statement, the thing we started with. Now, you may ask, why is it inside of this other function called slash mbox? Well, right now we're in mathematics. We're typesetting as if it were a mathematical equation, but I just want a plain word. And mbox stands for math box, is a box where you can type regular stuff inside of math. So the explanations will, if you didn't put the mbox there, I guess I'll show you this. If that didn't have the mbox and it just said the words given, but the word given was there, let's recompile. And let me make the output giant so you can see what happens. Do you see how the word given got rendered? Hard to highlight that. Well, I broke something. Well, anyway, you can see how the word given is rendered. It's all in italics. Probably not what we meant. What happened is LaTeX thinks you're in mathematics mode. So it thinks you've written the product of 5 variables, G, I, V, E, and N. You know, it's just a computer. It can't figure out that you were suddenly switching over to doing typing English. So it thinks that's a bunch of variables strung together. All right, so we really did need that slash mbox around here. Okay, then I did the various steps, and in each line I said what justified that line. I think did I just actually do one of the examples we just already did? I believe this is one of the examples we did by hand. So let's see how it looks once we're done. Oh, we can recompile so it looks, the given isn't all italicized anymore. I think that's a pretty reasonable way to format it. You could do other things. I often like to leave more space in between the lines than is present here, but that's getting a little bit fine. All right, so I think that's a great place to call it a day. I hope that the ending stuff about LaTeX was useful to some folks, and well, in any case, have a good rest of your day.